Welcome to part 2 of 2 on our lecture of conceptualization and measurement. So let's go right in from our previous discussion. On the last part, we were talking about test standardization and the information that was derived from something like the development of the IQ scale, the Wechsler Adult Intelligence Scale. So there's a larger concept that we need to talk about called the normal curve. So the normal curve is something that is observed over and over in regards to not just human behavior, but really various types of data that we gather. Many traits amongst human beings especially are attributed along the normal curve. And it's the most common type of data distribution that we see. So when I go out and I gather information about some characteristic of human behavior, processing speed on a test of cognition, IQ, whatever it is, what I find is that if I plot those scores, if I have a big sample, especially the bigger the better, if I plot those scores, they will typically distribute in this very consistent way called the quote-unquote normal curve. It's also known as the bell curve, and we'll talk about why. It's due to the shape, and we're going to look at one in just a moment. It is shaped like a bell, and there's a reason that's representative of how things are typically distributed amongst human beings. It's called a normal distribution or a normal curve. What's really the defining characteristic of a normal curve is that most scores fall somewhere near the center, the mean, the average, and gradually fewer scores as you go further out. Okay, so being way better or way worse than the average person becomes more and more rare as you go further away from the mean. So it's called the bell curve from that distribution that it has, and we're going to look at one in a second. The empirical rule is really what's used to help us understand important things about how the percentages of characteristics are broken down within the bell curve. This is how it typically is described, and I'm going to look at this in just one moment. So let's talk about it first in sort of a narrative way, and then we'll visually see it. But what the empirical rule says is that if you have a set of normally distributed data, something that falls naturally onto the bell curve, approximately 68 of all values fall within plus or minus one standard deviation of the mean. So about 2/3 of people will be within one or two standard deviations of the mean, pretty close to the mean. Approximately 95% of all human values fall within plus or minus two standard deviations of the mean. And then 99.7% of all values fall within plus or minus three standard deviations of the mean. We're going to look at this visually in a moment. But what this essentially means is that if you are scoring, for example, on the IQ scale, 3 standard deviations above the mean, that is extremely rare. If you are scoring 3 standard deviations below the mean, that is also extremely rare. And we'll talk about what we do with that information, how we make sense of it in a moment. So let's just look at a bell curve. This is actually the IQ scale that comes from the Wechsler, from the WAIS 4. So on an IQ scale, on the WAIS at least, 100, as I mentioned, is the mean. It's the average. So a score of 100 is considered, an average IQ score, right in the middle of this bell curve, as you see there. It has a standard deviation of 15 points. So as you go right or left, up or down the scale, 15 is the standard deviation. So from 100 to 115 down to 85 is within one standard deviation of the mean. And what you find is 2/3 of people, that bump in the bell curve, that large hump there, are going to fall in that distribution, right? So what does this mean? Well, in a certain sense, this means that more people tend to be average than abnormal, than extraordinary, right? The further out you are, positive or negative, it becomes rarer and rarer. You go within 2 standard deviations of the mean, we have 70 and 130, right? We've now gone 2 standard deviations, or 15 times 2, 30 points in either direction. We now have 95% of people captured under the curve right here. Now, within sort of clinical psychology, if someone has an IQ below 70, that is where we generally draw the line for what we call mental retardation. So the idea is that this person is displaying a significant deficit compared to the average person. Only about, a little over 2% of people, 2.5%, fall on that side of the curve. Now, the same is true in the opposite direction. Now, they used to always bandy around this term that 140 IQ is genius. I think first and foremost, that's based upon the Stanford-Binet scale, not the WAIS. But more importantly, it's just an arbitrary distinction of a number, right, somewhere. If you look at this, you could say 145 puts you 2 standard deviations above the mean. But remember, genius, quote unquote, genius, is just a qualitative label, right? It's really just a distinction of how rare that level of intelligence is based upon this particular definition, this particular operational definition of what it means to be intelligent. So let's talk a little bit about how we evaluate a measurement. So someone decides to take a hypothetical construct, something that's, doesn't exist in the material world, and they operationalize it somehow. Well, we have to evaluate that process of measurement. We want to say, how good a job does this test do? Does this measure do? So for a test to be meaningful and useful, it has to be both reliable and valid. So remember, we talked about this a little bit in chapter 1. Reliability essentially means consistency of results, and validity refers more to the accuracy, is the thing measuring what it is intended to measure. One way we talk about reliability is of measurements. How reliable is a measure? How consistent? So it's affected less by measurement error or chance variation. Okay. If it's affected strongly by measurement error, just noise within the data, so to speak, chance variation, randomly people can score with a lot of variability, just depending on the day, or depending on that moment, then it's an unreliable test. So you want consistent measures, and reliability, remember, is a prerequisite for measurement validity. Let's go back to our example of the scale we talked about in previous lectures. If I have a bathroom scale and I want to say, is it accurate? Is it actually weighing what I weigh? Well, that is really a question about validity, right? If I could, look at a crystal ball and in some perfect subjective way know that I weigh exactly 200 pounds, I just know that as a fact, right, somehow. Or I go to some atomic, super calibrated scale and it says that I'm exactly 200.000 pounds, then I want my bathroom scale to show 200 pounds when that's what I weigh. I want it to be valid. If it just wildly fluctuates because it's a badly designed scale, and some days it says 205 and some days it says 195, it's not reliable, and therefore it cannot be valid. So reliability is a prerequisite for validity. And a measurement's reliability can be assessed in a few different ways, and there's some different techniques we've developed to sort of make sense of this, and we're going to talk about each of those in the next slide. So the first thing we can use to evaluate the reliability of a measure is its stability over time. So the scale, I'm 200 pounds, does it read 200 now, 200 an hour from now, 200 2 hours from now, right? Is it reliably? And that's what's called test retest reliability. So when we think that a construct is constant over time, now that's an important assumption, right? For example, IQ is not really thought to fluctuate that much. You can influence it a little bit over the course of life through education and exposure to certain things, both positively and negatively. Through deprivation, you can see someone's IQ as they're developing actually go down a little bit based upon their potential and then what they get as far as their treatment over time with education especially. But ultimately, it's thought to be a pretty consistent measure of it doesn't change a lot over your lifetime. If I believe that about my construct, in this case we're using IQ as an example, then those scores should remain consistent over time. If I give you the intelligence test today and I give it to you 2 years later, it should show very similar scores. It has what's called a very high test retest reliability. So you should see similar scores each time. There is one problem with this in some tests, is what's called the practice effect. Once you become familiar with the questions, the first administration of the test is where you're first seeing it, it affects how you respond on subsequent administration of the same test. If I give you the IQ test now and I give it to you a week later, you're going to remember what a lot of the questions are, and that's going to affect the reliability of measurement. So some tests, it's not because they're bad tests. Exposure and the practice effect of having seen the questions influences the ability to have good test retest reliability. So there's a couple of ways to do that. We'll talk about some tests use what are called alternate forms, right? They're considered equivalent but different. That's one example of how you try to handle that. So you can take two slightly different forms of the test, different sets of questions, but measuring the same construct, very similar matched questions, and you can use that to measure the retest reliability of an exam or a measure, which avoids practice effects. Especially if you've got to give the retest soon after the first one, then you want to choose something that has alternate forms. If I'm going to measure your intelligence or something else today, and I'm going to measure it a month or a week from now, I might want to consider utilizing an alternate form. That way I don't have the practice effect. Another way we measure the reliability of a measurement is what's called inter-observer reliability, which is where you have multiple people rating or coding the same behavior. So let's say that you're studying aggression in school children, and you have a researcher that you're hiring to go and observe a very specific set of behaviors. You've got, beforehand, you've laid out these criteria and said, well, check this box if the person is verbally aggressive, check this box for every observation of, physical aggression, and you have a good operational definition of what that means, right? What you want to be concerned about is if I give that form to two different people, do they give me similar responses watching the same thing? Okay, that's inter-observer reliability. Or it's not a very reliable measure if that's not the case. If maybe it's vaguely worded, maybe it's not clear, maybe the instructions are poor, right? And maybe they're too subjective. Maybe they don't give people a clear indication of what to report, what not to report. So this is something that we look for. We want to see that inter-observer reliability to show that a measure is not really affected by bias of the individual and what they bring to that measure. If two observers are watching a competition, for example, you want them to assign scores in a similar manner. When you have more than two rates, when you have like more than two people, when it's multiple raters, you can utilize something called the intra-class correlation coefficient. This is one way to assess inter-observer reliability, and it's the equivalent to what would be the average test-retest correlation between all the pairs of tests kind of thrown together. So you look at every possible combination amongst all of the different raters, and then you kind of get an average of that. Another type of reliability we look for in a measurement is what's called internal consistency reliability. So a lot of times when we're measuring a construct, we have multiple questions that are trying to get at the same thing. So let's look at a real world example you might have seen before. There's a measurement called the PHQ-9, the Personal Health Questionnaire 9. Now, the Personal Health Questionnaire name is really kind of intended to avoid confirmation bias. What it really is it's a measurement of depression. But it's called the Patient Health Questionnaire 9 because it has 9 questions on it, and you don't want to tip your hat to you're not just asking them, are you depressed, are you not depressed? You're a little concerned about bias. Is the person going to, want to make themselves look better than they are just out of, some degree of shame or embarrassment? Are they going to fake bad because they're trying to get out of something? So you don't call it what it is, right? There's a little bit of deception built in. You call it the Patient Health Questionnaire 9. That test is, that measurement is really derived from the 9 criteria within the Diagnostics and Statistic Manual, the DSM, which is the big Bible of psychiatric disorders that we utilize within the clinical psychology world. All of the diagnoses for things like depression, schizophrenia, substance abuse, it's all in there. Right? It's all in that book. Well, there are 9 criteria that we associate with major depressive episode, and the Patient Health Questionnaire 9 simply asks you to rate on a scale those 9 questions. The PHQ-9 has what's called good internal consistency reliability. This is where the individual questions within a measure, they should highly correlate with one another, right? Correlate, they should co-vary. As a person reports one symptom of depression, it should be somewhat more likely they're going to report another, right? That they should hang together in a meaningful way statistically. This is called inter-item reliability. And when you're the more specific the thing you're measuring is, now depression, it has a lot of components, it has a lot of aspects to it. But if you're measuring something very specific, you should really want to see high inter-item reliability. An example, if 5 items on a test measure levels of aggressiveness, you could say that test had high inter-item reliability if all 5 of those items indicated similar levels of actual aggressiveness. And there's many different ways we can do this. There's statistical tests we can use to measure this. One is called split half reliability. That's where you simply randomly, like let's say there's 10 questions on a test, you randomly split it into 5 and 5, and then you assess the correlation statistically between those two groups. How much do they covary? As one goes up, does the other go up? That kind of thing. This is called the split half reliability coefficient. Now, as you can imagine, by randomly selecting, especially on a small measure with only a few items, just by random chance, you could end up with some weird matchups there that don't make a lot of sense. The way that you get around that is you utilize something that's more thorough called Cronbach's alpha. It's just one statistic you can derive from a measure that has multiple questions on it. What it does is it sort of does every possible iteration, like every possible way I could randomly split this into two halves, and it runs all of those options and gives you sort of the average of all those options. So it's a very meaningful and helpful statistic when you're looking at a measurement, especially when you're developing a new one, to know if it has internal consistency, if the items are all touching on the same construct in a good way. There are various ways in which we can increase the reliability of our measurements. A very simple way, interestingly enough, is to just make it longer, right? This is you're adding to the number of blind men that are assessing the elephant, right? So that you're getting more and more data, and therefore you're increasing reliability. That's one way to do it. So by simply just adding more questions that are still thought logically to make sense and coherently stick together on that one construct that you're measuring, you just add more questions and you get better reliability over time. So by adding items, you're increasing inter-item reliability because you're reducing random error, right? There's an example of 3 different types of test-retest reliability for the measurements of subjective well-being in this chapter in Exhibit 5.12 in your book. So we've talked very briefly about correlation, and I've used that term a lot. We're going to do an entire chapter on correlational studies, but I want to give you a brief refresher on what I mean. This is your little stats corner for this chapter, okay? So we compute through a specific formula the correlation between two things. It shows us basically how closely related these things are, how they covary. So these are scatter plots. Scatter plots are where you have 2 pieces of data for an individual, a subject, whatever, a person in a study, X and Y, right? And these can be any 2 things: height and weight, aggressiveness and history of violence, whatever it is. These things that you're interested in. Aggression as a characteristic, for example, in history of violence. What you're really getting at is, I want to know, as one goes up, does the other go up in a systematic way? As one goes up, does the other go down in a systematic way? As I increase socioeconomic status, do I increase education level, for example, right? Whatever it is you're studying. When we have a set of data for individuals, what we can often do to see if there's a correlation visually is we plot it on a simple X and Y axis, right? So whatever that person's score is, we find it on one scale, then we find their score on the other scale, and we plot that as a point of data. And these are examples of those points of data. So what we've got here is what's called a positive correlation. As you can see, all of the data is really hanging along this line, right? It is very consistent. As X goes up, Y goes up. If you're very low on X, then you're very low on Y. If you're very high on X, you're very high on Y. This is what's called a positive correlation. As one characteristic increases, the other increases as well. What you can sometimes see is the inverse, but still very meaningful relationship of what's called a negative correlation. As your level of X goes up, your level of Y goes down consistently. Again, the data sort of hovers around a line that we can just sort of visualize running through the middle of it, right? This is an example of an absence of correlation. There are some people that are high on X but low on Y. There's some that are high on X and high on Y, and everything in between, all combination. This would be considered essentially no relationship in this scatter diagram. Let me go back into a few details about that I want to talk about. So I'll just include it on this slide, but basically we utilize a symbol. The statistic correlation that we run, the actual stat spits out something that is it's a single lowercase r. Okay, we use lowercase r to symbolize correlation. That's because it's developed from a specific statistician who that's what he symbolized it as. It's called, and so as you can imagine, it ranges from 0 to 1 and 0 to -1. So really from -1 to 1, right? Uh, you can have a 1.0 positive correlation, which means that in a very specific way, it should go up 1 increment on x, should go up 1 increment on y. You can have a perfect -1.0, which that second scatter plot represent, where very consistently as you go up on x, you go down on y, and vice versa. Or you could have 0, which means that there's no relationship, it's random. So it's really a way to quantify reliability in when we're looking how things are measured. We want to see consistency in that relationship between those variables. So now we're going to talk about the logic of measurement validity. So remember, we've got reliability and validity. Reliability is a necessary component to have validity, but it really talks more about consistency of measurement. Validity, if you remember, is really about how accurate our measurement is. So we evaluate a construct's validity by determining whether its multiple indicators cohere into a predictable and logical pattern of relationships, right? Within our theoretical understanding of that construct, does that measure consistently seem to tap into it in all the different parts of it very well? So a valid measure does what it is purported or supposed to do. For example, the Wechsler intelligence scale is considered, this is debatable, but it's largely considered to be a valid measure of intelligence, meaning it is measuring something that we agree upon to be the construct of intelligence, or it's making an attempt to do it well, accurately. There are various types of validity that I want to talk about here, and we'll go into each one. But basically what we have here is face validity, content validity, criterion validity, and construct validity. We're going to talk about each of these in detail. So face validity is, you've heard the term that something is valid on its face. There's also a legal term called prima facie. This is a Latin expression that means on first appearance or at first sight. But basically a face validity is saying, does the measure just kind of appear to measure what it's intended to? So to the average person who's looking at it, can they say, oh yeah, this is a measurement of depression, or this is a measurement of intelligence? Like, does it make sense intuitively, right? It really lacks a firm scientific basis. It's just kind of saying how the impression that it gives, but it's not really scientific in that sense. It's obviously subject to a lot of biases, including what's called social desirability, and it can be a really serious threat to a self-report measure. If it doesn't have face validity, just on its surface, it can be confusing to the person that's taking it. Now, remember, sometimes it's important to have some deception. You might not want your test to have face validity on occasion, but generally speaking, you want the person to understand basically what these questions are getting at, what they're trying to measure. So that's one form of perhaps the lowest form of measurement validity. Another is content validity. And this is really saying, does the measurement have sufficient breadth to capture the full range of a construct? Okay. If it doesn't capture important parts of that construct, important aspects of its definition, especially within a theory, then it does not have good content validity. It's missing pieces. For example, going back to our metaphor of the blind men and the elephant, if you're only examining the trunk of the elephant, you are missing large parts of what makes the elephant an elephant, right? You're only getting a piece of it, so you're lacking in significant content. So the Wechsler scale has 10 core subtests or subsets within it, and this is basically based upon the theory that drove the development of the test. They broke intelligence down into 10 aspects, 10 types or components of intelligence, and you can look at the Wechsler and see that it does touch on all 10 of those in a meaningful way. So it's really trying to get enough content to capture the larger construct. In some of the research that was discussed earlier in the chapter, Keyes uses multiple measurements to capture the full range of mental health. Keyes was the one who defined subjective well-being by sort of the absence of mental health issues, right? Mental health problems. And he used multiple measurements to get at that. So he captured a lot of different things that could be present, and by their absence, he then, inferred that the person was mentally healthy, potentially happy. Criterion validity is really the extent to which a test score agrees with some other objective criterion, some other objective measurement that we think represents the thing. Here's an example that's from the substance abuse research world: the extent to which self-reported feelings of intoxication agree with a blood alcohol test, right? If you want to say, is a blood alcohol test, a BAC, is that test a valid measurement of intoxication? Okay, because of course this has large implications for things like drunk driving, right? If we're going to utilize blood alcohol test, what I want to see is that as that blood alcohol test level goes up, does it correlate with the person's self-reported feelings of intoxication, right? If their BAC is very low, is the person saying they have minimal indication or very mild symptoms, so to speak, of feeling intoxicated? If the BAC is very high, are they subjectively reporting feelings of intoxication? So does it relate to that objective criterion very well? In this case, BAC is my hard test, right? BAC is my actual blood content. If I'm asking people to self-report intoxication, I want to make sure that if they say, oh, I'm 0 on 10, that their BAC is relatively low. If they say they're 7 or 8 on 10, their BAC is relatively high. I want to go to some objective thing like blood alcohol content to see if my other measure has criterion validity. Oftentimes what we'll do is we measure that objective criteria at the same time. So in the alcohol example, what we do is we say, okay, on a scale of 0 to 10, tell us how intoxicated you feel. Of course, we're also measuring that person's alcohol intake in that setting. And then we get a BAC reading. We have them do a breathalyzer. So we now have these two measurements. We have this sort of subjective one we've developed, this self-report one we've developed, and we have an actual objective criterion. We can then correlate those two things, and if it has a strong positive correlation, as the person's self-report of intoxication goes up, their BAC goes up in a consistent and reliable manner, we can call that concurrent validity, right? It's valid concurrently. You can also do this if it's predicting something in the future. So in the concurrent validity example, we're measuring two things at the same point in time: self-report of intoxication and BAC level. Let's use the SAT as an example of predictive validity. Now, you take the SAT before you go to college, obviously, right? So there's a time distinction between when the SAT is given and what it is intended to predict, which is college performance or success. If I want to evaluate whether or not the SAT has good measurement validity, good criterion validity, what I can do is I can look at your SAT score and I can see how it correlates with your college performance, say 4 years down the road, okay, or a year down the road, 2 years, whatever, at some point in the future when you're in college and how you perform. If it does, then I might say that the SAT has good predictive validity, right? The thing it's trying to measure or predict in this case is college success, and it does a decent job of that. So criterion validity is a really good indicator of a measure's validity, but it's not always attainable. Sometimes there is no way to objectively measure that thing. And I want to give you a couple of examples. Happiness, right? The subjective well-being idea. There is no Star Trek level technology that I can swipe across your forehead that says, oh, this person is at 74% happiness. We don't have an objective criteria to compare some of these scales that we discussed in the chapter 2. Another is the pain scale. The pain scale is a very frustrating thing that I utilize a lot with patients because many of my patients have health issues. That's the world I work in geriatrics and primary care, and a lot of them deal with chronic pain. There's no magic, device that I can run across a person's forehead that says this person is in 7 of 10 out of pain. It's highly subjective. There is no criterion that I can then correlate the pain scale. How are you feeling today on a scale of 0 to 10 in terms of pain? I don't have an objective criterion. So it's a great way to measure validity of a measurement, but it's not always available. Another type of validity and measurement is construct validity. It's the extent to which the theoretical framework and the empirical framework of the construct are valid. This is a little bit confusing, but ultimately we want to say whether or not these measurements match nicely within this theoretical or empirical framework that we've built up about this construct, right? This thing we can't really truly measure. There are various ways to do this. One of them, which is somewhat complex, is called the multi-trait, multi-method matrix. This is a way of measuring construct validity, and you see this a lot when people are developing a new measurement, a new device, a new test of some sort. And you do this in this weird way within this matrix. You assess with two different you want to look at two different things. There's the thing you're interested in, the trait you're interested in, and then you want to measure something else, another type of trait. Okay, that's one grid to the matrix, right? To the x and y. That's one axis. Is you have two measurements of two different things in a similar way. You use a similar type of measurement. So I may have one that's measuring intelligence and one that's just measuring performance, right? Something similar but unrelated in terms of the content. And then I want to utilize two methods for each of those. So I want to give an IQ test, and I also want to give some other test of intelligence. I want to give a performance test, but I also want to go get a report from their employer about their job performance, for example. Multi-trait, two different traits, performance and IQ. Multi-method, two different techniques. That's where you get your 2x2 matrix here. If you measure the same trait in two different ways, and you get a good correlation, as it should, because you're measuring the same thing with two methods, you're looking for something called convergent validity. You want to see those two measurements of the same thing correlate highly and converge. So IQ scores and behavioral observations of intelligence by teachers or parents. You should get similar scores, right? Convergent validity. That tells me that my IQ test is doing a decent job, a valid job, an accurate job of tapping into this construct of intelligence. If I use a similar method to measure two different things, those things should not perfectly correlate. They should discriminate or have discriminant validity. So if I measure IQ score and extroversion utilizing similar types of tests, those should be unrelated because they're not the same thing construct-wise. They're not the same concept that we're thinking about. So that's where we get to the idea of utilizing discriminant validity. There's an example in your book, Exhibit 5.15, that really goes into great detail about the multi-trait, multi-method, but we'll leave it there for this purposes of this lecture. Another way that we can look at construct validity is something called latent variable models. Now this is going to get a little bit in the weeds as far as statistics are concerned, so I'm really just going to give you sort of the 30,000 foot perspective on this if I can. We can infer and develop and evaluate our construct models through something called latent variable models. It's a statistical technique. It's where you basically are breaking down your measurement statistically in various ways. One of them is called factor analysis. This is the most common type of latent variable model, which is able to identify dimensions or factors within a construct. The WAIS-4 has this model. So you have this overall rating of intelligence, but you also have four distinct factors that you can find. So verbal comprehension, perceptual reasoning, working memory, and processing speed are the four major subtypes of intelligence within the WAIS-4 theoretical model. If you take all the questions on the WAIS-4 and you run them through what's called a factor analysis, so you take a person's performance and you have all that information, then you have maybe 100 or 1,000 or 10,000 people, you run it through a statistical model, and what it does is it loads that question onto one category or another. So it shows you that you've got these factors, these like subtypes that are meaningful statistically within the larger construct. And if your theory says, hey, I think that intelligence is made up of these four things, you want to see plenty of questions loading on each factor. It's also it's used in this way for what's called confirmatory factor analysis, right? This is where you say, I think I know the parts of this construct. I want to see if my measurement is valid, if it touches on all those parts, if it loads naturally onto those parts. So the more similar the scores, the more likely it is that that set of items taps into a particular factor. And you can do this with a second independent sample and then get this confirmation as confirmatory factor analysis. But these indicators or variables are these objective responses to the questions, and you have this extensive sample of thousands and thousands of IQ tests within the psychometric development of the IQ test. And it's just basically factor analysis in these, which is one type of latent variable model. It allows you to sort of uncover and coalesce the extent to which people respond similarly and within these sort of confines. Let's talk a little bit just for a moment. I think it's important anytime we're talking about psychometrics and especially about the IQ test that we talk about culture and how it's affected in measurement. We know that measurements can be biased, and specifically we know that some forms of IQ testing are particularly biased against certain cultures and ethnicities. A groundbreaking study by Steele and Aronson in 1995 demonstrated how negative stereotypes, which is called a genetic deficit, have been traditionally used to explain racial IQ differences. And in a sense, what they're saying is that the development of the IQ test was done in a culturally insensitive or a way that was focused more on sort of quote unquote mainstream, or in this case, white culture at the time. And so it actually produced lower scores in African Americans, not because African Americans are less intelligent, because the test itself is biased against them. This is called the stereotype threat, and it's something we have to be very careful about when we're developing tests, right? It's something that we need to consider, because not just to be politically correct, right? This is not what this is about. It's about wanting accuracy and validity. There is a moral and humanistic thing to be considered here, which I think is a very good reason to develop tests and ways of studying human behavior that are not biased. But just from a simple empirical scientific perspective, you need to pay attention to this in test development, because you want to be valid in your measurement of intelligence. You don't want the cultural context, specifically sort of a culture that is biased against African Americans, to be error entered into your measurement of intelligence. You want to actually measure intelligence. So we have to be mindful of cultural and stereotype threats that can come in. So as I said, there's strong evidence that the disparity in IQ we used to measure between different races was really due to environmental and social factors, not to any real genetic or biological difference between people of different races. Because, as we know from further and further research, the entire concept of races is kind of ridiculous, right? It's cultural. It's not real. Based upon DNA, there's really nothing uniquely distinct about us in terms of how we define people as a certain race or another. So, to conclude for a moment, researchers formulate and manipulate and evaluate constructs which are formed conceptually, right? They start off hypothetical, to analyze variables of interest operationally. We have to take that step from hypothetical concept to objective operational definition that we can actually measure. Most importantly, so we can practically analyze numerical data with statistics. The levels of measurement that we use have large implications for what types of tests we can use. What it is we're studying sometimes dictates what sort of level of measurement we need to use, which one is logically valid, what makes sense. And finally, we need to be, recognize that we need validity and reliability within our tests for them to be trustworthy. For us to have any trust or faith in the outcomes, that what we're doing is good science, we have to start with tools that are reliable and valid, right? You want a good tool to begin the process. If you've ever built anything, I do a lot of woodworking myself, but like the idea of, if you've got a dull instrument or you've got a misaligned or miscalibrated tool, those problems just compound down the line, and the end result is worse and worse and worse. So it's so important that we pay attention to the reliability and the validity of our measures. And then finally, when we're developing these tests, we're doing our best to utilize good hard science. We always have to be mindful of how culture and how stereotype threats can come along and influence the validity of our outcomes. So we need to account for those things. We need to examine them. And of course, in test construction, we need to try and control for them and eliminate them as much as possible.